In this video, we're going to consider a very important concept from chemistry, and that concept is called equilibrium. So let's do this by example. If I take hydrogen chloride gas and dissolve it in water, I will create the hydronium ion and the chloride ion. Now, in this equation, we have a basic acid-base reaction. The HCl has donated its H plus to the water to create hydronium, and the chloride ion is what remains. So notice that chloride has a minus charge. Therefore, the H that left was actually H plus, which is nothing more than a proton. So this is an acid-base reaction, and in particular, HCl is considered a strong acid. Now, on the other hand, suppose I react acetic acid, and this is a common way to write acetic acid with water. I will use a different symbol. I will use the double arrow, and this creates hydronium plus acetate ion, which is like chloride ion. The difference is this. In the second reaction, we use the double arrow, which is called in equilibrium with, to emphasize the fact that the back reaction, the fact that hydronium ion can react with acetate to give me acetic acid and water, is at least just as important as the forward reaction. In the first case, essentially all of the HCl in water goes to hydronium plus chloride ion. And this is the difference between, in the first case, a reaction that goes to completion, and in the second case, a reaction that is in equilibrium. Now, one thing I want to emphasize here is that the first reaction does not go completely 100% from reactants to products. When they're done, there's still a little HCl and a little water left. But the critical thing to realize is that we are interested in the production of hydronium ion if we're talking about an acid-base behavior. So the little bit that's been left off is insignificant. In other words, it occurs in a significant figure far down the line. On the other hand, in this case, this equilibrium lies very much on the side of acetic acid. In other words, when you're done, what's mostly in this solution is acetic acid and water. There is very little hydronium and acetate that have been produced. But chemists always have a preference, if you will. The reaction we draw as the forward reaction, in this case the top arrow, is the reaction that we are most interested in. The back reaction, the one that corresponds to the reverse arrow, is one that happens whether we like it or not. So in this case, we are still interested in the production of hydronium ion, despite the fact that very little of the HOAC is converted to hydronium. Now, if the reaction goes to completion, we can just use normal principles of stoichiometry to calculate how much hydronium and chloride we produce. The problem is, in equilibrium, that's much harder because, in the end, you have a little bit of everything. So instead, we use what's called an equilibrium constant. And I will give you an example of one right now. In particular, the equilibrium constant for a weak acid is something called Ka. And it can be written as the concentration of hydronium ion times the concentration of acetic acid divided by the concentration of acetic acid. This concentration up here was the concentration of acetate. Now notice here I have put the names of the species in square brackets. This denotes concentration of. So in other words, this is not the acetate ion, rather it is the concentration of the acetate ion, probably measured in molarity. This constant, called the acid equilibrium constant, or K, simply Ka, is a number that can be looked up in a book. So what it says, as this reaction proceeds one way or the other, let's look at the forward direction. As it proceeds in the forward direction, we produce more hydronium and more acetate ion, and we end up with less acetic acid. So this would get bigger as it runs in the forward direction. Similarly, if I go in the reverse direction, this would get smaller. Now, since this has a value we can look up in a book at 25 degrees Celsius, that means that there is a value. There is a point in this chemical reaction where the reaction appears to stop. Okay? And at that point, you will have a particular concentration of hydronium and acetate and acetic acid. Okay? And that is the point of equilibrium. Now, suppose I were to add some sodium acetate to the solution. Okay? Now what that means is I would take sodium acetate and dissolve it in water, and I would produce sodium ion and acetate ion. Okay? Now, since I have added acetate ion to the solution, and if we go back to let's write our Ka expression again. So we have Ka is equal to hydronium plus acetate divided by acetic acid. Okay, since I have added acetate ion, the numerator has gotten bigger all by itself. In order for this to still have the same value of K, the reaction would have to run backwards. In other words, it would have to run in this direction, where we're reacting acetate plus hydronium to give me HOAC plus water. Okay? That is the back reaction on the previous equilibrium. As this proceeds, I lose this and make some of that so that I can reestablish the equilibrium. In other words, this will get, as soon as I add the acetate, this is bigger than it should be. If I run this reaction, the acetate goes away and the HOAC comes back, so this becomes smaller. This is an example of what's called Le Chatelier's principle. Namely that an equilibrium will always shift to minimize the impact of a change to the system. So in this case, I had a big change in the system by adding a bunch of acetate. This system will respond by chewing up the acetate and turning it onto acetic acid. So it reestablishes the equilibrium defined by the equilibrium constant. Okay? Most chemical reactions actually are controlled by an equilibrium. So this is not something, a special little side point we want to make. This is going to be typical of most of chemistry, and how you will especially see this in Gen Chem will be in the study of weak acids and bases.